non-secure task. And there was a question at the end, I don't know who the gentleman was, but at the end, there's a question from the audience about using the non-secure scheduler to schedule things. And then there was, in a previous tech forum meeting, I saw some slides with FreeRTOS work on the non-secure partition manager, and but the slide was pretty light on details, and so I'm not sure exactly where we're at on as far as TFM is at on that work and what exactly it means. All right, so proposal overview, there's a couple of slides here.
Eric, just
yeah.
We just managed to start the recording. Before you move ahead, could you just show the slide number 1? So then it remains in the recording.
Yeah, thanks, Abhishek. Yeah, I also would like to break and announce that, yeah.
That's great, thanks. I think we should just move on.
Okay. Okay, so back to the overview of the proposal. Again, this is an overview. Implementation details may be worked out. In thinking through it, we haven't come across any blocking issues that we think couldn't be, things that couldn't be overcome. So the first part of the proposal is to use the TZ context APIs. So these have already been defined as part of CMSys core, okay, but actually go and implement them as they appear to have been designed for, which is to switch stacks or contexts on the secure side based on what the non-secure side RTOS is doing. And then in addition to that, to provide some, what I'm referring to as basic task synchronization APIs for the secure processing environment to communicate with the RTOS. So these would only be semaphore mutex, okay, so semaphore pin and post, mutex take and give. Some RTOS is essentially, that's the same thing, okay, but that's an RTOS level detail. So what's left out of this would be things like queues and FIFOs. Some RTOSs, like FreeRTOS, has a direct to task notification API, which is more efficient. But there were nothing in this proposal about supporting things like that. Okay, so you have basic semaphore mutex APIs. And this API would provide a common implementation on the secure side to take care of some of the security issues, and then the porting layer could actually be on the non-secure side. That's getting a little bit into implementation details, but that is something we've thought through based on some of the feedback we've already received. So those two changes should allow a non-secure RTOS to schedule its tasks even when its tasks have been called into PSA root trust functions. And with that, then we can reduce our blocking times down to minimum times needed to protect the memory mapped I/O and shared states, which is typically how systems are done today when you don't have TFM or PSA implementation. Everything's just kind of in one non-trusty context, right? You would, to get a more responsive system, you would minimize your blocking times here. Okay, so this slide is mostly about how you go from non-secure to secure and that interaction. And this part of the proposal is how you handle application root trust. So each application root trust partition would also be given a PSA root trust stack. Okay, and then the SPM would need to be kind of solely responsible then if it was going to enter an application root trust partition and that app root trust requests a PSA root trust service, the SPM would have all the information it needed to do the stack switch as part of the context switch. Okay, and this would be needed for isolation level 2 or greater in the PSA security model. Now, each application root trust partition could still have their own single stack internal to the partition, and in that way, it's just like the IPC model. There's an alternative, and there was some discussion on the email list on this, where you could have the application root trusts work like the PSA root trust would, where they have a stack per non-secure task. I don't mention it here, but they need a stack actually per user, right? So if you have 2 application root trusts and one can request a service of another, you need a dedicated stack for that as well. Now, obviously, okay, that starts using a lot of RAM. Okay, so one of the optimizations, we'll get into this later, is to how to cut back a little bit. That would be one, one of the downsides of this proposal is you're going to use more RAM because you're using all these additional stacks. So there's a trade-off there. Also, care would be needed to keep confidentiality when making that non-secure to secure call for those APIs to support the synchronization. And then, one of the nice things about, and there was a little bit of a discussion on this this morning on the email list. So one of the nice things about the existing models is they're simple, right? As far as the security analysis goes, they're pretty straightforward. I got an event loop. As soon as I enter that event loop, hey, I'm locking a resource. I don't have to worry about anything jumping into back into this code when I'm halfway through some sort of operation. So now we're giving more flexibility about when you take and give these locks. Now, a particular implementation of some root of trust service, right, could still choose to put the mutex right at the entry of the code and release it right at the end, right? But now you have the option to kind of move it in if you want. But if you're going to do that right, you need to be careful about that. In addition, one thing that would need to be part of the implementation is actually keeping a lock state in the SPM for each of those mutexes. So even though the non-secure side, RTOS, right, will have some sort of state being kept for a mutex, we can't trust that. We can't trust the untrusted RTOS to be honest about that mutex state. So there has to be some duplicated state, if you will, in the SPM that would guard against the RTOS being malicious and claiming that a mutex is free when it's not actually. If you don't have that in here, then there's some pretty straightforward attacks. So, if an application root trust was requesting PSA root trust service and the mutex is taken, and then there's an interrupt and you actually transfer the non-secure side, and you have a task there that requests the same root trust service. If the RTOS is solely responsible for keeping that state, it could report that, hey, it's free, and then its request for the root trust service would go through, potentially destroying the integrity of the application root trust request, and certainly giving opportunities for some confidentiality issues. I don't have any diagrams for that. Hopefully that's clear. We can revisit that if needed in any of it, of course, if anyone didn't understand something. Okay. So some possible optimizations. So every non-secure task, right, may not actually request root of trust functions. And if that's the case, you actually don't need a stack for it dedicated on the secure side. So we could have a null context. So essentially, when the TZ context APIs, of course, have a load and store context API. Those are two different calls. So when you call store, it would store the context information off in the SPM and then load a quote-unquote null context. There might be a better name for that, but essentially what would happen then is if a request for a root trust function occurred while that context was the present one, then you would take an appropriate action. So perhaps a common error code would be returned, or the SPM could simply panic. Kind of a similar idea, you could save some save some RAM for your stacks dedicated to the application root trust by sharing the same PSA root trust stacks. Now, obviously, there's a spectrum here. There's a trade-off of, okay, I can use more RAM for all these stacks, and that's simpler, okay, as far as within this proposal goes. Or I can start doing some optimizations to save some memory, but I'm increasing complexity. There will be a trade-off there. Everyone on the call, I'm sure, is familiar with the concept that complexity is an enemy of security. So yeah, going back to the IPC and library models, they are simple. That's a good thing from a security standpoint. I still believe we have this gap for accommodating existing systems, and that limits the potential adoption for this technology. Really quickly, and this is my last slide, TFM project implications. I don't know that we need to actually have in TFM the RTOS synchronization APIs. those could be adopted in TFM, or at least the spec for them, right? And that'll become part of the standard for TFM. But at a minimum, I think we would need to have the TZ context APIs support the stack context switching, and that the SPM needs a mutex implementation. Now, I put this build in here, I'll admit, on the mutex implementation without going back and revisiting the SPM code to see if something like that's already there. It may be, but those are the two things in this proposal that would really, I believe, need to be present in the TFM to enable at the platform level to achieve this proposal's goals. Okay, again, other than the a trademark notice here, that concludes the presentation. I'm happy to take questions and have a discussion on it.
Yeah, thank you, Eric. Yeah, there was quite intensive discussion on mailing list just before the forum time. So I think this is the easy and best time to discuss this proposal. Anyone wants to start?
Yeah, hello.
Okay,
Eric,
hello.
can you hear me? Yeah. So I have some confused in your proposal. You said the application route and the PSA route. Here's the PSA route. The PSAFF set the secure partition routes has two tabs. One is the application route and the one is the PSA route. So you said in this presentation is the can you back to the I think the third page?
Third page.
No.
Page?
No. The 5. The next one?
Page 5.
Yeah. Oh no.
No,
yeah.
Sorry. This one here, slide 5.
Yeah. So you mean the first the first one use the same systems TZ context API to provide a PSA route stack. So here the PSA route stack is what I have said the other types route PSA route. Yeah. Not for the application route. Or you mean it is just a secure service here?
Yeah, so this would be for the, so this is for the PSA root trust. And your question, I think, is what happens when the non-secure task wants to access an application root trust? Is that where we're going?
Yeah. So you mean it's a PSA root? Yeah.
Yeah, so this would be for the PSA root trust. If the non-secure side wants to access the application root trust, then there's an option here, okay? And I don't have a solid direction on this at this point, but I don't know if you can see my laser pointer icon here. The second bullet, the application root trust could still have its own single stack, okay? So it works just like the IPC model, or you could have the application root trust have a stack per non-secure task, right? So in that case, if it's the second option in the TZ context, when it does the switch, it wouldn't just be switching. Sorry, if I get my slides to go back. It wouldn't just be switching for the PSA root trust stack. It would actually be switching out a stack dedicated to the non-secure task, and that stack would be used when it accesses the application root trust or the PSA root trust. Now, if you go down that road, right, you may have some issues with the isolation level 2 and 3 that would need to be worked out, but you'd still have isolation level 1. So that would be an implementation issue or detail to work out. So I don't have those details. That needs more time to think through that or collect feedback. But if you had if this was really just for the PSA root trust, then when you have the application root trust still use the existing IPC model, right? Then you'd have the level 2 and level 3 isolation. That's pretty straightforward to achieve.
Okay. So you know in PSAFF sites there are not all the secure partition can be accessed accessed by the non-secure side. That means that some secure partition only be can be caught in the secure side. Yeah. So for this service, I think you cannot short address by the NSPE ATOS, I think. Do you think about that before?
No, I didn't consider the implications of services not being accessible from the non-secure side. But what can you explain more about what the consequences of that would be for this model?
I'm not sure. I'm not sure only the application. Maybe the PSA root also can be accessed in the secure side, I think. Yeah. Yeah, maybe we can discuss more about that offline. Okay.
Okay. Yeah. I'll take a note and certainly add that to the list of things to consider to make sure that we're not violating any expectations there. I think off the top of my head, if something is not accessible, is not supposed to be accessible from the non-secure side,
Mm-hmm.
then you just need to. There may be an implication for the stack space and how much stack space you need. You may be able to reduce that, but you just need to block the call, right? So either you don't have, if you're doing some sort of veneer implementation, you simply wouldn't have a non-secure callable veneer. And if you're going over an RPC or IPC call mechanism, right, you would need some sort of guard in that mechanism to block the call and say, no, I can't do the non-secure is not allowed to invoke this function, which I believe already exists in the IPC model for the day. I believe it does that check.
Okay.
So it'd be something I would imagine something similar would be present for that.
Mm-hmm. Okay.
Okay. From my understanding, looks like the so this is not working for the RPC model, right? This is a new model, and it looks like the application root partitions got their own stack, and it looks like at least the PSA root partition or root service are working under the library mode. Is that a correct understanding or something?
Can you say that last part? Or at least the PSA root is doing what?
Looks like the PSA root services are working on the library model, right?
I think that's right.
Yeah, just with a dedicated stack. Yeah. Which I don't think is, and maybe that was part of the library model and I just missed that, but I didn't see where the library model, at least not as implemented today, supports a stack per.
Well, I think he means as opposed to IPC. You're not using IPC to go from non-secure to secure. You're just calling a function.
Yes. Okay. Yeah. Yeah. If that's what's meant, then yes. Correct.
Mm-hmm.
Okay, so the application root partition is working on it's working like the library model or the IPC model. Since I saw there's a line that said that it has its own stack.
Yeah. So this is on slide 6. This is not a firm part of the proposal. I've got this as kind of a primary direction, which would be just like the IPC model, but the alternative listed there would then essentially be the library model.
Okay.
Okay, and this is not, for me, this part of it is personally a little bit lower. It's lower priority in thinking through this proposal, honestly, because for our use cases, it's more around the use of the crypto, which is in the PSA root trust stack that we're trying to solve some some problems with that, right? So while we do have some potential use cases for application root trusts, those aren't as firmed up yet. So I don't have a good feel for which of those two alternatives I have in this proposal would really work best long term.
Okay. Can you tell us something more about the Mutex implementation in the SPM?
Yeah. So, well, yeah, I'm not sure maybe exactly what you're wanting to know about that, but the kind of a standard mutex implementation. But it's in this case, if it's a there needs to be a way for that mutex.
So to be simple, I want to ask, where the SPM Mutex implementation involves a secure to non-secure call, something like that.
Yes, that's correct. Yeah. Yeah. So it involves a secure non-secure call. So for these mutexes, so let's say you wanted to for the take, right? It would be very similar for the give, but for the take call, it would need to check the state of the mutex on the secure side, okay, in an atomic manner, and if it's not already taken, it would update that state on the secure side, and then it's going to need to signal, okay, and that would need to be most likely done through some interrupt handling, okay. It'll need to signal over to sorry, forget the interrupt handling. I was thinking of some force there for a second. So you need to update the state, and then you do a secure to non-secure call, all right? And of course, as part of that, you need to secure the registers, right? So the code running on the secure side would take care of pushing or clearing out the registers get pushed, but it needs to clear their states to 0 before it actually does the call to the non-secure side. If I recall correctly, the hardware does not actually clear the registers for you. So you do that, and then you would make the call, and then it would need to be a standard. Well, what I'm proposing is that that's a standard call to the non-secure side. So the non-secure RTOS needs to would provide a standard set of APIs. Okay, so at this point you would not be getting into the RTOS specific call, but you would be calling a TFM defined API that is implemented on the non-secure side. And then that code on the non-secure side then takes care of translating the parameters into the RTOS specific mutex call. And then once you get into the RTOS call, right, then it's up to the RTOS to handle and do the scheduling, all that. By keeping the state also on the secure side, then when a task had been blocked waiting for a mutex to be freed, if it gets rescheduled by the non-secure side and starts executing, the first thing it would do is it would check the secure side state for that mutex, and if it's not as expected, if it's still locked, then you would need to have an appropriate response. So there's a way to signal an error, or you panic, or something like that, because that indicates that, maliciously or not, some sort of state corruption has occurred. Does that explain more about what you were looking for, or do you have further questions?
Yeah. Thanks. I got more details.
Okay.
Well, that describes the first half of it. That's how the secure thread blocks using a non-secure primitive. But then how do we go about unblocking that thread?
So the unblocking the thread when you do when the thread is it actually becomes blocked by the non-secure operating system, right? It's actually in the non-secure state. So when it resumes, it's actually resuming in the non-secure state and then does a return, and it actually returns back to the secure side, right? So now it's back to the secure side. The secure side is going to do the state check, like I just said, and then assuming everything is fine, it will continue execution. Am I missing something there, Alan?
Well, yeah, I was trying to give you the hardball question of what process triggers the unblocking. I mean, assuming that it's some secure interrupt that goes off that the secure service is waiting for, how does that secure interrupt notify the non-secure RTOS that it's time to unblock that thread? That's the tricky part.
Right. So switching kind of to the semaphore case where you've got so we have a hardware accelerator. We're waiting for an interrupt to indicate that some operation by the hardware is done. The secure side interrupt handler will need to post to the semaphore. Now this is a semaphore that is part of the non-secure RTOS, and the secure interrupts would need to use a non-secure interrupt to signal over to the non-secure side to post the semaphore on its behalf. All right, and then that has some implications to the interrupt priority. So the interrupt being used on the non-secure side would need to have a lower priority than the interrupt on the secure side, where the interrupt on the secure side will actually finish first, so you don't have some stacking issues on the secure side. And then the result of the posting the semaphore would let the RTOS know that which task is now ready to execute, and it would do the context switch. And that's very similar to how I described the context switch based on the new text just a second ago.
Right. Right.
Yeah. Yeah. Okay. So there's additional overhead over what you have in a non-secure system. If you're a non-secure system, right? But that's to be expected. We're not thinking that we can get away with no additional latency for these operations, but we want to minimize the blocking times, and again, simplify what what our customers, as a chip vendor, what our customers have to think through when it comes to scheduling, right? They're used to, I have an RTOS that has one scheduler, and I have a set of tasks so I can set their priorities, and then they will work in that manner. And so we have customers that are used to that way of thinking, and so we're looking to continue to support that, where they continue to operate in that manner and not have to, as I said before, kind of really rethink how their system works from a scheduling standpoint.
All right. Is there any other concerns, questions, or ideas?
So just a question from my side, Sobi here. So is this model expected to be another model officially supported from PSA, or is it just a TFM implementation thing and it just remains part of TFM? It's not part of PSA.
Yeah. So, I don't know that, whether or not it's part of PSA. I don't know. In this context, we're talking about TFM. I think at a minimum, with from what I understand from the code base, and certainly Alan's done help me out with this part, is that we'd want to see these two things be present in the TFM code base, right? It might be hard at a platform level to add these things on if those first two things, the easy context APIs, being able to switch out the stacks, and having mutex implementation on the SPM side, I'm not sure that the current build system would support us adding that at the platform level in an easy way. Right. So those of you that are more into the the day-to-day code modifications to TFM, I'm sure would have some solid ideas on how this could be accomplished. Right. But either it would be something to make it easy to add on to TFM, right? So that way you can maybe have the some of that stuff from the TFM code base working side by side with this model, right? But it's being done at a platform level, or you have some of it pulled actually into the TFM to enable that to where the platform can take care of the rest of it. And where that dividing line is, I'm not entirely sure, but we'd be looking for some feedback on where we could draw that line to make this something that we could accomplish. Right?
Okay, yeah, I get it now. Thanks.
So I'm wondering, why can't this coexist side by side with the IPC model? If we fleshed out the implementations of the TZ context APIs to do something, to do what they're expected to do, can there be additional veneers that the non-secure side can call into the secure side, and those veneers, those threads have this additional functionality that they can block using these primitives that you've described? Now, can that peacefully coexist with a PSA firmware framework model that the IPC build model supports, or does that directly violate some PSA spec somewhere? You see what I'm saying? So that would allow us to say that we are fully PSA FF compliant, but in addition, for certain operations that require certain performance behaviors, we have separate veneers that can also block. We have some secure threads that can block in a normal non-secure RTOS manner.
Yeah, I see this proposal as a combination between something in the middle between library and IPC. Just out of top of my head, I do not see implication on PSA certification. So please correct me if somebody see anything.
Well, there is some language in the PSA firmware framework document that says these are the only APIs you can invoke going from non-secure to secure. You can, those 5 PSA calls are the only thing that are allowed.
Right.
And this would say, no, we're adding our own veneers, and those veneers can block. And that would be the concern about whether we would still be PSA FF compliant or not.
Yes, I think to clarify a little bit there, so I think, there's being compliant or with the the FF document, and there's the PSA certification, right? So I don't think this runs afoul of the PSA certification, but it may, if implemented, be like, well, okay, this isn't a fully PSA firmware framework compliant implementation at this point. Which I don't know if that's a deal breaker. I know the TFM has the library and the IPC model. IPC model is firmware framework compliant. If the TFM code base can handle this, as someone just said, it's kind of halfway between the IPC and library model to add a little bit of flexibility in here. Hopefully it wouldn't add too much code or maintenance burden. Then it would give, I think, a lot of people a solid code base to start from if they have these kinds of use cases that we're facing.
Yeah, all right. And can we compare kind of benefits and what's the pros and cons of this approach? True. I see you are proposing is it's more, it's faster. Means there's kind of response time is reduced. It's not non-blocking calls. So partially you reduce the memory use in the RAM memory. So what's the side effect of this? So bigger code, that doesn't look like.
I guess the biggest implication is the security implication, of the
Yeah.
secure side calling into non-secure and making sure that there is no concern over there. I guess Eric has already mentioned it should be fine, but I guess this is something that probably we need to make sure that this is all right. I think that's the biggest point of contention, but otherwise seems fine.
Yeah.
Hi, this is
Yeah, I
Andrew.
would
This is Andrew Tolga here. I'm just gonna. I've been watching this thread with some interest. So I developed the firmware framework specification, and this kind of model was certainly on the table when I was first looking at this, and the concern I had with this approach was that it definitely solves the I've got a long-running secure operation and I don't really want it to stop everything, including other secure operations which are not related to that one. So security service which doesn't need any of the same shared data should be able to run. But the problem with the simple model of an NSPE stack per NSPE task, that kind of is manageable, but you still have questions like, should the same SPE stack be used between different security services? Now, in isolation level 1, there's no concern about separating the services. It's just about keeping them separated from the non-secure world. So in a level 1 isolation, you could kind of build a runtime model that says, okay, we've got quite a few more stacks so that we've got a context on which we can run a service for a non-secure task that isn't running. And the major downside is that you now have concurrent execution in secure side, and concurrent code is much harder to get right. And code that isn't right is vulnerable, has significant risk of vulnerabilities. So there's a lot more care required to get this right before you even start thinking about, okay, I have got shared data. I now need a synchronization primitive to control use of this shared resource, whether it's a piece of hardware or just some data in the secure environment. And obviously, you've considered the complexities of asking the non-secure OS to run the mutex, or at least essentially the wait queues that are involved with that. Which means the secure side can't trust the non-secure side to tell it when a resource is actually in use. But it's the complexity of dealing with concurrent access to shared data was my main concern with pursuing that. Plus, once you go to the isolation level 2 or 3, then you have significant additional scaling issues with, okay, now I've got 2 different contexts, application root of trust, non-secure environment, that both want to use a PSA root of trust service. And so how many stacks do I need now? Do I use do I need, for every non-secure task that asks an application root of trust service to talk to a PSA root of trust service, is that now 3 stacks? And it's easier to write down that you need these stacks, and then it's hard at runtime to go, well, where do I find them all? Where do I find all the memory for this? And how do I manage the setting up these contexts? And does an application root of trust service have 1 stack, or does it have 1 stack for every non-secure task that asks it to do, that makes a request? And I think the problem space gets hard to reason about for level 2 or 3 isolation without putting some abstractions in place. And that's what the IPC model does. It says, right, we're going to solve the problem of trying to get one-to-one association of stacks and calling contexts by actually making each partition its own execution environment and having its own thread of execution. That requires you to have the concept of some form of scheduling, which could be quite lightweight, but still some form of scheduling, and sort of a less direct mechanism for invoking remote calls. But at level 1 isolation, I can see the argument that says I want my system to be just that little bit better or more responsive, or able to deal with scenarios where I've got hardware acceleration for certain things, and I don't want to commit all the resources required to basically jump to the IPC model. Level 2 or 3 isolation, I would recommend taking more time over, because I think the complexities of, you know, multiple steps through the secure environment makes the provision of stack frames and making sure they retain sort of confidentiality and integrity. So you don't really want stacks shared between the PSA root of trust and the application root of trust, as you identified. And unless the system has a very small number of tasks and threads in it, then there's a kind of explosion of memory required. So at the time I defined the IPC model, and the TFM team developed the library mode, and I suggested keeping library mode simple because it's possible to at least actually get it running, keep it secure. And then the question was, is there even something in between? And this is a proposal to say, can we have something that's in between? And I'd recommend not making it too sophisticated on the first outing, but it still might be worth exploring what it would look like in a level 1 isolation system.
Yeah, I think that's fair. Yeah, I appreciate and like the simplicity of the IPC model as far as how it constrains the problem to make it a lot easier to think about the problem of security. I think it's a great design. It just unfortunately doesn't fit some of the use cases we're trying to solve because of the blocking issues, which is unfortunate, right? If we weren't faced with these kind of issues, we wouldn't be proposing something. We'd just be using the firmware framework as is and be excited to do it. But yeah, totally understand and I think agree that starting with isolation level 1 and then spending more time on what isolation level 2 and 3 would look like. Now, I guess that'd be a question for the TFM code base. Would that be an acceptable change to the TFM code base to introduce this model, but constrict it to level 1 isolation for now, and say that, you know, level 2, level 3 work would be ongoing to see if it could be accomplished in a way that the organization is comfortable with and confident will provide the security guarantees that customers will be looking to this code to provide. Will that be or is it a written or spoken requirement that all the models need to support all of the isolation levels? I'm not familiar enough with the TFM process to know the answer to that question, so I'm looking for answers to that.
I believe this is up to us how to manage the code and which model to use in which case. So currently we use 2 models and we support 2 levels of isolation, so we can introduce separately, but I think it will create extra concern of the security and extra cost and extra testing. So here I would support Andrew, who's saying like simplicity might be a better solution, even if the cost of the efficiency to address the security problem. So having the complex design, have a cost of.
Sorry, I just wanted to answer one of your questions that So currently there is no such requirement that all models should support all possible isolation levels because, for example, the library mode doesn't support isolation levels higher than 1. And as far as we are concerned, there are no plans to do that, so no plans to support higher levels of isolations. And one thing I was thinking about that introducing a third working model for TFM core, so the code base is quite, so managing these two models in parallel in the code is quite a complex task already. So naming, so the most practical issues that naming codes using conditional compiling in some files depending on the current model I used. So, and I'm also not sure how widely adopted the library model itself is. So we might also consider, instead of introducing this one or thinking of this one as a third model, maybe we might, yeah, we might basically think of discontinuing the library mode and introducing this as a second model next to or parallel to the IPC model that is we probably want to continue supporting, because the whole PSA program or so basically replacing library model with model something similar to this. At least we can, or we might discuss this, I think.
Thank you, Matteo.
You could just add this functionality to the library model. So the library functions can now block if they need to.
Yeah, you could just treat it, you could kind of treat it as an upgrade to the library model.
Yeah.
Actually, yeah.
Considering the time, we have about 1 minute, or a little bit more than 1 minute time. And it looks like we cannot conclude anything on this forum, but yeah, it's good what we see this presentation and have this preliminary first discussion about it. I propose to continue this discussion on a mailing list, which already started. And if it's necessary on the consequent course or on technical forum, we can get back to this idea and discuss it again, so what we want to do. And meanwhile, I have a question to Eric or Alan. So do you start working on it as a kind of concept or prototype or something? So you can
yeah, I've actually prototyped the basic mechanism for the secure side to call out into the non-secure side and block on an RTOS semaphore. And then later on, when the secure interrupt goes off, to trigger a non-secure interrupt that is dedicated to unblocking that semaphore that the original thread was blocked on, and confirming that all behaves like I expect it to. The next level of testing would be to flesh out the TZ context APIs in the TFM code base, because right now they're all stubbed out for the IPC model, and to make them do something, and do the allocation of the stacks, the switching of the stacks, and demonstrate to myself that you can have multiple threads calling into the secure side. Get rid of that gate that blocks everything from going from non-secure to secure. Get rid of that, and then show that you can have multiple threads go in, and they could all block, and they could all unblock. So there's been a certain amount of prototyping of this already has done.
So maybe you can share this prototype if it will be on some stable state with the community, so and the community can review and propose and help you with this direction. This is my proposal.
Okay.
Eric, I had one question for you because you suggested that there are some use cases for which the IPC model doesn't work, and I'd just be interested to have a bit more information about those use cases because I've got plans to work on and update the firmware framework, and if we can include additions that make those use cases work, then that's something I'd like to consider.
I think one of the major concerns is the time that it takes to go from non-secure to secure. By the time you get to the secure partition that's going to handle the service, 2,000 cycles have gone by. So that's
that's
huge
one
overhead.
That's one concern, and then the other concern really quickly is you start thinking about connected devices. And things like mesh networks where you have a lot of communication and you potentially have different concurrent connections, and you may have some connections that are actually supposed to run at a higher priority than the other connections, right? So if an event occurs for one connection, it needs to be able to respond within a certain time frame, and so the longer blocking times of the IPC model is part of what kind of really gets in the way of that, right? So if I've got a PKA operation running that might take tens or hundreds of milliseconds, right? Well, I can't even encrypt, 100-byte AES packet until that's done, right? So that kind of thing is where we're at. We have the latency, like Alan mentioned, that causes challenges for us. Then we also have the IPC model. Again, not knocking it, right? It's a great model, but it's not the most responsive model, right? So we're looking for a system that has greater responsiveness in terms of scheduling.
Yeah, I want to once again bring to our attention. So we are out of time, and I think some participants might have another meeting, so other plans. So I
really appreciate all the feedback and the opportunity to present today. Thanks.
Yeah, thanks. Thank you, Eric, for presenting this. Yeah, thanks everybody for questions, for comments on this topic. Yeah, again, I'm inviting you to the mailing list to continue this discussion. And thanks everybody. So I'm closing this forum for today. Yeah, have a good day and stay healthy this time.
Yeah, thank you.
Goodbye.
Thank you.
Thank you.
Thanks.
Bye.
Bye-bye.
Thank you.
Thank you, Eric. Thank you, Alan.
Bye.
Bye.